Welcome back, everybody. Let's continue on week 3, number 2, 0, 1 matrix. Given an m by n binary matrix, mat, return the distance of the nearest 0 for each cell. The distance between two adjacent cells is 1. So here's the example 1, and you see a matrix, and there's a single 1 in the middle. So that's going to be the distance between these zeros to this 1 would be 1. I think that's just a weird coincidence. Example 2. So you see another one. Let me make this more dominant. And there's a row of zeros, and then a 0, 1, 0, 1, 1, 1. Okay, so, let's just take it from this 0 here. Well, these approach zeros, so I guess they don't count. Let's start with this 0, right? So if I'm just going from this 0, this is a distance of 1, right? Distance of 1. This is a distance of 2. This would be a distance of 3. And this would be a distance of 3, right? So if you were to remake this, let's say there's a single 0 here. You'd go down, and it'd be a 1. You'd go down, it would be a 2. You go right, it would be a 3. You go left, and it would be a 3, right? From that single 0. Except that single 0 is not the only 0. There's a 0 right here as well, right? This red 0. And you can imagine that this red 0, let's say it's positioned here, right? This red 0 would make this a 1, so that would be the same. But it would go down here, and this could actually be a shorter distance. That would be a 1. It would go here, and that would be a distance of 2. So you could see that depending on which 0 you're starting from, the distance actually changes, right? So there's this dynamic where if this is the current distance, if there's another 0, right, then the update has to be the minimum of the current distance and, whichever the minimum of the current distance and what would we call this red one? And a new distance, I guess. So there's some dynamic where we possibly have to, do this for all the zeros, right? So let's say these are green. This 0 is green, right? And we have to go here. That's going to be a 1, and that's going to be a 1. Although these are already 0, so I guess you don't do anything if these are already 0. And these two green ones, let's make this a green, is also trapped, right? You go here, those are already zeros, so you don't do anything. And let's just go ahead and finish it up. This one will make it blue, and this blue 0 will look to the left, look to the right. That should be a distance of 1. It's already a 1. It will look down. This should be a distance of 1 also. That'll be a 1. And then from here to here, it's a distance of 2, right? So we don't need to update. So there's a dynamic, and I'm just going to write it down, where from zeros, update based on smallest distance, right? So this is a dynamic that we have here. And this is a pretty realistic problem, right? It's realistic because let's say you're building a game or something, right? And there's some units or some positions here. And let's say somebody throws a fireball, and the fireball, blows up here and here and here and here and here. And then, based on some distance, maybe people get the effects of the fireball, right? Yeah, or maybe some smoke or something, or they get some damage, right? So you're, making a video game. There's a person here, he's not damaged. The person here, he's not damaged. Person here, he's not damaged. But maybe the person right here is damaged a lot, right? And that person gets like a, negative 100 life points, right? So this is a pretty realistic problem if you think about some grid world where, from a certain number of positions, this one, this position, this position, this position, this position, this position, we need to emanate some damage out based on some distance that somebody is standing next to it, right? And you could imagine there's another example where maybe there's a, tsunami or something, and then the water, can only flow a certain amount, and the people standing there, or maybe it's music, and some people can hear it, some people can't, based on some distance, right? So, don't let them tell you that Leetcode is always useless. This would be very useful if you're doing a 2D grid world type of thing. Okay, so how would we code this? Well, for one, the most confusing part about this is the fact that these are zeros and these are ones, right? Because when we're talking about updating this distance, we want this to represent a distance, and we represent it in this yellow one, right? So this yellow one is representing a distance. When we go downwards, we want this to be a 2, but there's already a 1 here, and it's just confusing, right? So, something that would be, for me at least, less confusing is instead of zeros and ones, this was, literally anything else. Literally anything else that wasn't a number, right? Where this would be like, we'll put F for fire, right? And then these ones were like P for people, right? And the fire goes a certain distance, right? So this one would go a distance 1. This one would go a distance 2. And I wouldn't be so confused about the P and the I wouldn't be so confused about the difference between a 1 and a 0. So instead of a P, because we have to do a comparison anyway, I think what would be better than P is if we change this to some maximum value, right? So let's say it's infinity, 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 infinity. So when we're looking at, the F going downwards, as long as the distance 1 is smaller than infinity, then we can swap it, right? So it's smaller, we swap it. We go downwards, as long as this distance 2 is smaller than infinity, we swap it, right? So this is a 2. But this also works the same the other way, right? This F from this F, if we go downwards, this is a distance 1, it's smaller than infinity, we swap it. And that's because it's infinity, right? But what if from here, from this one right here, we went this way? Well, from here, if we go that way, it's a 3, right? And because it's smaller than infinity, we swap it. That's a 3 now. But if this F right here goes downwards, well, this F's distance is smaller than 3, and it's a 1. So we swap that one, right? So, from every F, we can basically do a breadth first search, where we're always going one step away from the F, one step away from the F, one step away from the F. And if we ever find a position there that's smaller or larger, right, this 3, then we can go ahead and do the swap, right? And if it's not smaller, we can end this iteration. So this is basically what we're going to do in the code, right? This diagram right here. Maybe we don't need to change these to F's, like maybe these can stay zeros, but we probably want to turn these into infinities, right? So step 1 here would be change 1 to infinity. It doesn't have to be exactly infinity. If you think about it, there's a maximum number that this could be, right? So given a grid like this, there's a maximum distance from here to here. The maximum distance is 1 step, 2 steps, 3 steps, 4 steps, 5 steps, 6 steps, right? And if this is an m by n, depending on which one's m and which one's n, then you can imagine this is 4 plus 4 would be the maximum, right? M plus n would be the maximum. So that's a fairly good one too. So it's either infinity or n plus n. I actually don't mind which one it is. Okay, so we change ones to n plus n, and then we want to do a breadth first search starting from every 0, right? So for every 0, we're going to enqueue into a, put it in the queue, the 4 directional moves, right? So the 4 directional moves would be up, down, left, right. And that's the 4 directions we want to go. So, given a single 0, we want to go up, down, left, right. And then after we enqueue it all, while there's a queue, while there's elements in the queue, we want to go ahead and pop, right? And then we do a visit, right? So after we pop, if the element at that position is well, I guess there's a lot of things we want to do. First, we want to check if it's in bounds. So check in bounds, else, return, and I guess check if it's 0, else, return, and then we check if the number is already smaller, right? So if you're looking at this 0, you're going to somewhere where the position is 1, right? But this one's a long time coming. This one's all the way up here, right? So the distance from here to here would be 1, here to here would be 2, and here to here would be 3, but there's already a 1 here. So if there's already a 1, you kind of want to exit early and say some other 0 is close enough that sets it to a lower number. So check if x is larger, right? And if it's larger, we return. And then otherwise, right, else, we do a visit. And the visit is update, and then the 4D, right? So this is basically what I drew here. It's exactly what I drew here, just written out, right? Except, what I drew did not check out of bounds. Right here, you don't want to do that out of bounds. You don't want to do out of bounds in any direction. And you don't want to do it if it's a 0. You don't want to do it if it's larger. And then else you complete the iteration. All right, so I think this gives us a really good base, right? We've have an understanding of the spatial aspect of this. Basically understand the different steps here, and let's see if we can put this into code. Okay, I'm going to go ahead and pull it up here. Move this a little bit, and let's see it. Okay, so what we have in the diagram, let's just make a note of it, right? Let's put some comments here. So first things first, we want to change the 1s to infinity, right? Or n plus n, either one. The next thing we want to do is for every 0, we want to enqueue it in some type of queue, right? And we want to enqueue the 4 directions, right? So we want to enqueue up, down, left, right, and then we want to iterate. So while there's a queue, we want to do a couple things, right? So we want to pop, we want to check, so if out of bounds, right? Exit, right? So if the element at position, right, is 0, then we also want to exit. And then if another 0 has come here before and has had a smaller number, so if the x, I'm going to call it, is larger than element at position, then we also want to exit. Otherwise, we visit, right? We visit, update if needed, and then we also want to go in the 4 directions, right? So the 4D, up, down, left, right. And I guess we can think of some edge cases here. I guess we can also we can always handle the matrix being empty case. So if the length of the matrix is 0, then we always want to return, I guess, an empty matrix. Okay. Let's do the first one. Let's change 1 to infinity, or this larger number. So we have a list of lists right here in the matrix. In line 2, you can see that the type of this is a list of integers. So we're going to want to do a nested for loop in order to iterate through all of them, right? So in range, and we're going to do the length of the matrix. So let's think about why we're doing the length of the matrix. The length of the matrix, if you look at this example, is going to represent the number of rows that you have, right? So this is an iteration where I is the index of rows. And then we're going to do another iteration where we're going to take the first row and we're going to get the length of that, right? So if we have the length of this first row, we have the number of columns, right? So I is going to be row, J is going to be column. And I believe we can just prove that out by getting the element here, right? And if you wanted to see it, you can print ij and the element. If we run this on an example, hopefully this will be the same example, 0, 0, 0, 0, 1, 0. You'll see that this is I, this is J, sorry, ij, and the element 0, I, J, so 1, so 0, 1, the element's also 0, I, first row, J, the last one, element's also 0, I, J, and then here, the element which is actually 1, in this example, will be 1, 1, right? The first row, not the first row, one index row, which is the second row, and then the second column is going to be that 1. Okay, so what do we want to check here? So if the element is 1, right, then we want to set this element to m plus n. We can go ahead and do that one. And what is m plus n? Let's call this a max number of moves, right, from one end to the other end, and that's going to be the length of the matrix, which is number of rows, plus the length of the matrix at 0, which is the number of columns. And we set this to the max number of moves. And that's the max if you're not backtracking, right? If you can go backwards and forwards and backwards and forwards, then that's truly infinity. You can do that forever. Otherwise, we want to enqueue something. So for every 0, we enqueue it. We do it in all these directions, right? So, well, I guess that means we need a queue. We don't have a queue yet, so let's go ahead and add a queue somewhere. And in Python, this is going to be a dequeue. It's going to be a double-ended queue. It's going to allow us to pop and pop left in constant time. So what does it mean to enqueue everything? Well, we want to queue append, right? And we're going to append a tuple here. And that tuple is going to be at least, it's going to be something like this, right? IJ, and the distance is going to be 1. Right, so it's, you know, so why do we need a distance? It's good. The distance is these numbers right here. Right, so as you're going down one step, you're always adding it by 1, right? 1 to 2, 2 to 3, you're adding it by 1. Right, that should make sense. Okay, so which way is going up? Well, going up is, it's I minus 1, right? That's going up. Going down is going to be I plus 1. Going left is going to be j minus 1. And going right is going to be j plus 1. And they're all going to start at a 1 distance, right? Okay. So go ahead and close this. Yeah, we go ahead and basically just code this, right? So while there's a queue, so while the queue, or if you want to be more explicit, while the length of the queue is larger than 0, we want to do this one right here, right? Number 3. So x pop, what does x pop mean? So x equals pop, and we're actually going to want to pop left, right? We're going to want to pop left. That's going to take the first element that's in the queue, and this is a method of the queue, so we're going to do this. And what's going to be here? It's going to be that tuple, right? It's going to be this one right here, and the tuple is going to be I, j, and distance. And because it's a tuple and it's Python, you can actually just assign it like this, I, j, and distance, and that's totally fine. Okay, so check and bounds. Check if it's out of bounds. Okay, so how do you check if something's out of bounds? Well, if I is smaller than 0, so if it's -1, -2, -3, it's out of bounds. And if I is larger than, what would I be larger than? I is the row, so I would be larger than the number of rows that we have. What's the number of rows that we have? I guess we can save it here. So number of rows that we have is going to be the matrix. It's going to be the length of the matrix, right? Let's just make this more clear. So this is the row index. This is the column index. Okay, so the row index, column index, row index, still the row index. And if the row index is larger, I guess, or equal to the number of rows, then this is a row out of bounds. Right, so let's just continue the while loop in this case. We're going to need a column out of bounds. Column out of bounds is basically the same thing, right? Column is less than 0. And the column is greater than or equal to the number of columns. How many columns are there? Well, just like we saw here on line 9 on this n plus m, it's going to be that length of any single row, right? So the matrix at 0. So if this is greater than or equal to number of columns, then we also want to continue. And what else do we have here? If 0. Okay, so if this thing is 0, how do we check that? So if the matrix at this row I, at this column I equals 0, then I guess we also continue, right? We skip it, right? I guess we could have changed this to F, right? Could have been the fire. 0 works as well. Could have been the tsunami. Could have been the concert music. Could have been anything. Some element that we're not trying to change, right? Whereas we're trying to change the other ones because the other ones are, you know, not the entity that's causing this distance check. Anyway, so if it's 0, we can go ahead and continue. All right. So this last one right here, this else right here, this is the one that we have to care about, right? So, oh wait, no, we're missing one. Check if x is larger. Oh, okay. So if the element here if the current element is, should we check if it's larger or smaller? If these are all, we're trying to do continues, it's actually not that it's larger. You see right here, let's check if x is larger. But if the current element is larger, then we can exit early, right? So if the current element here is it larger or smaller? The current element, what leads us to continue? Is it larger or is it smaller? Let's look at the diagram. So if we have the current element here is a 3, and we've moved from, let's say, a 6 position down to a 7 position, and we're looking here, the current element is a 3. So if the current element is smaller than our distance, then we can, you know, stop. Or I guess if it's equal to, if it's equal to our distance, we can continue, right? Perfect. And yeah, so in this case, this is the else case. We want to do the update, right? And the update means that we're going to go ahead and change this. And we're going to change this because we're confident that the distance is not equal to or larger than, it's actually smaller than, right? So at this point, we know that the distance is smaller. We want to do the distance. And then we also here, at this point, do the 4D, right? We want to go and enqueue the 4D. And this is the 4 directions, right? So same as the code from above, we want to append. And there's going to be a tuple here. And it's going to be the row of I, column of I, and then distance plus 1. Copy this 3 times. We want to go up. Up means -1 here. We want to go down. Down means +1. We want to go left, which means -1. We want to go right, which means +1. All right. So here we have many continues. This will help us exit early. Go ahead and delete this. We've done all of this, so I can go ahead and delete this. It's actually in the code now. Don't need to print this. This is also in the code. Aha! And we want to return something, right? So what do we want to return? We want to return this matrix that we've changed. We've mutated the matrix. Aha! List is out of range. So you got to be very careful. We have an if row and column equals 0, but I have to check that that this, okay, so I've checked that this is in bounds, right? If rho is smaller than 0 and it's at least larger than, and if it's equal to or larger than this, the length of the matrix, which is the number of rows, the column out of bounds, column is smaller than 0, and it's larger than the length of columns. So at this point, the matrix should be fine. But even, let's see. So iterate through here. And then here is for the number of columns. Yep, that's fine. I have that element here. I set this matrix to some max number. Then I append these into this queue here. And then I get this number of rows. So I wonder which value is, I want to do this without consoling too much. You have to practice doing this in your head because in some environments they won't give you a REPL. You won't be able to run your code. So if the length is larger than 0, right? Is this range correct? Should be correct, going from 0 to there. So this would be going from 0 to the length of the matrix. So 1, 2, 0, 1, 2. The length of the matrix would be 3. It would go up to 3, but it won't be inclusive. This one will go up to 3, but it won't be inclusive. Right. And the reason we know that is because, I should have kept a print here, but the reason we know that is because of this, right? I'm not going to try that yet. Okay, let's look at this code and wonder why this index would be out of range at this line. Because at this line, we've already checked if it's in range right here. I see. There's a bug here. So when I'm checking out of bounds, I'm checking that these are and. The row is both smaller than 0 and larger than the number of rows. And that's not going to happen. This is OR for sure. Right? This is also OR. I think that's one possible case here. Yeah. Yeah, that's definitely one possible case. So I'm going to run this, and this will definitely fix that problem. There may be another problem. We don't know yet. These are not all the cases. There could be another problem hidden somewhere. So let's go ahead and run this. All right, so we beat some number of users, but what matters is the runtime here. So what's the runtime? So if there's m of n, then we're at least doing O of m times n for this section, right? Because we're doing all these changes. And then we append everything into every direction. And then for every direction, it's like m times n times 4. Because for every one of these, we at least go in 4 directions. Something like that. But yes, for every one of the zeros, in the worst case, we travel I guess in the worst possible case, we traverse the whole thing multiple times, right? So this is a 0, maybe these are zeros, and we keep propagating downwards for every one of the zeros that exist. In the worst case, I guess in the best case, they're all zeros, and then there's not that much propagation because it's an early exit. Then it would be m times n times 4. I guess in another case, there's just 1 0. It has to propagate every direction. I guess in another case, there's many zeros, and it sets it up where it's constantly propagating. I think it's still linear to the length of the matrix, so it's actually not. It's not too much time. All right. I'll double check on the runtime thing, but this was a pretty good solution. I think you basically were here for all of the logic and the run through of why we did it the way we did. We could maybe approach it another way where we could be more selective about which zeros we're propagating, be more selective about not going out of bounds. And maybe we could combine these two while loops. I wouldn't try. This is a pretty good way to answer it. Thanks for coming. Thanks for watching me reason through this problem. I will post this video, and if people want, I can post these diagrams as well, and you can have it some other time. Thank you so much. Please leave a comment on any problems that you want to see that are not on this list. Go ahead and check this off, and I'll see you next time.